Welcome back. In today's lecture, we are going to discuss maximum work and entropy of ideal gas, and with some certain examples to illustrate our understanding and or rather to test our understanding. So, let us look at this combined first and second law on this single phase and simple systems. Okay, so what we have is a similar kind of geometry which we have discussed earlier. So, you have the insulated regions which is in a shaded form, piston cylinder geometry, and this is a flow system, and this is a non-insulated, hence heat can be transferred here. Okay, so there is an inlet and as well as there is an outlet in this case. So, this is a very generic open system. Now, what we are considering is that this is internally reversible, okay, quasi-static process with mass entering and leaving a system. Okay. Under this condition, the T in is going to be T out, and that must be T because of the fact that it is a quasi-static process, and similarly P in, P out should be equal to P. Okay. If you do a mass balance, then the change in the moles or in general mass is nothing but going to be simply the difference in these two entity, okay, which is delta of N in minus delta of N out. Now, let us apply the first law on the system here defined by this dash curve. Now, in this case we are ignoring the changes in the kinetic energy and the potential energy. So, what you have is dE is equal to du, and that would be your delta Q reversible minus any boundary work, or in this case that is here, okay, plus we do have a flow. So, essentially you have U plus PV dN. Okay. So, because of the mass, so this is the contribution due to the mass. So, that would be your U plus PV dN. Okay. So, that is the first law for the open system. Now, this now what we can do is we can try to relate this delta Q reversible to entropy. And how do we do that? So, let us first look at what is the changes in the entropy of the system, that is your ds. So, there will be two contributions, one due to the heat, okay, exchange or heat interaction, that will be simply your del Q reversed by T is constant here. So, the second part is the contribution to the mass flow, and that is why is written as is a specific entropy multiplied by the differential change in the moles, or if it is molar entropy, that will be multiplied by differential change in moles, or if it is specific entropy, then you have to consider this as mass. Now, what we can do is we can combine this expression with the previous one. Okay, we can rewrite, we can take this here and redo this, rearrange this expression and plug in this expression of del Q in this expression, and okay. So, this would be your TdS minus ST dN, right. So, this is nothing but del Q reversible. So, now if you plug in this, the TdS comes here, and we can take the minus Ts dN in this part. Okay, that is what is done here. So, this combined expression is now TdS minus PdV plus this molar internal energy plus PV bar, again molar volume, and then you have this molar entropy here multiplied by T, and then the whole expression is multiplied by dm. Now, we will define this mu, this is something which we will learn more about this expression or this particular variable mu. That is something very valuable in the later part of this course. So, mu, this is nothing but basically mu, because this is by default G, something which we have already discussed in the first week of this course. So, G bar, which is a molar G, sometimes we also write G here like this. So, mu is nothing but G, okay, and this is nothing but mu u bar plus PV minus Ts, and this can also be written as H minus Ts. So, by definition this would be mu. So, we plug in mu here. So, this is going to be mu dN. So, the final expression comes out to be this, and this is something which is true for open system. So, if this is not open system, of course you can keep plugging, this will go to 0, and in that case you will get back the original expression, which is nothing but du is equal to TdS minus PdV for quasi-static and slow process and equilibrium process. Okay, so for this will be true for closed system. So, what you have, this expression is for only open system, or you can consider this to be a generic expression. Okay. Alright, so if you have many components in the system, then you have to sum it up, mu I multiplied by dni. So, this is the generalized expression of du for open system, okay, with multiple component system. Okay. Now, u is indeed, from this u would become a function of s, v, n1, n2 and so forth. That is something which we have discussed in the first week also. So, that is something we can clearly see that you have also proved it from a basic analysis of your first law of thermodynamics, considering the relation of the entropy with the heat interactions and mass flow, and basically considering the basic definition of the chemical potential, you obtain the same expression as we have discussed earlier. Okay. So, let us move forward and talk about minimum and the maximum work, or the reversible work of expansion or compression in flow systems. Often engineers are interested in finding out what is the minimum amount of energy which is required for operating a device, or rather minimum amount of work required to operate a device, or the maximum amount of work that can be generated from a device. So, the relevant devices would be, for a compressor we would be interested in minimum amount of work required to operate, and for turbine the maximum amount of work which we can produce. So, these are the two important usual questions which comes in the mind of engineer, because we would like to minimize the energy required, overall cost is associated with energy, and we would like to maximize the energy and produce of course more value out of it. So, one can deduce the minimum energy, minimum and maximum amount of differential work for a given process in the following way. So, del W is basically nothing but the integral of the molar volume multiplied by the dP, and okay, and then you multiply by the differential amount of the moles which is passed through, let us say, a compressor. Okay. For the device operating at a steady state, you will write like this: W dot S is equal to N dot P1 P2 V dP. Now, this is something which you can prove it also, and if you have taken the earlier class of engineering thermodynamics, you would see this expression and the derivation as well. So, where this one is nothing but the power input, and N dot is nothing but the molar flow rate of the working fluid. Okay. So, which could be gas, which could be steam and so forth. So, we will do some examples on that later, but let us take different ways to understand this concept of maximum work, and this is something which is described by Callan. So, consider a system that is to be taken from a specified initial state to a final state. Okay. So, there are two ways we can work in. You can actually interact with the reversible heat source, or you can also interact with the reversible work source WRS. Okay. And the change in the internal energy is given in this way. So, what the maximum work theorem says that for all processes leading from the specified initial state to the specified final state of the primary system, the delivery of work, okay, which is in this case, is maximum for a reversible process. Furthermore, the delivery of work and or heat is identical for any or for every reversible process. Okay. Now, this is something very interesting. So, let us try to make use of this concept, and let us look at this a bit more in detail. So, by definition, Callan says that reversible work forces is defined as systems enclosed by adiabatic impermeable walls characterized by relaxation time of the system sufficiently short that all processes within them are essentially quasi-static. So, what it says that whatever you are doing associated with the devices, the equilibrium is reached so fast that they can be considered that at each moment you are moving from one point to another, you are basically undergoing a quasi-static process. Similarly, the reversible heat sources can be defined as the following: a system enclosed by rigid impermeable walls characterized by relaxation time sufficiently such that all processes within them are essentially quasi-static. Okay. So, one deals with the adiabatic impermeable wall, there is no heat interaction as far as the work device is concerned. The other talks about rigid impermeable wall, that means there is no movements of the boundaries when it comes to heat sources. Okay. So, but both of them should have relaxation time sufficiently short, so that they can be considered as quasi-static. Now, let us look at the mathematical relation of this diagrammatic way of representation of interactions of the system with the reversible heat source and reversible work source. So, let us look at the first law. So, you have, by definition you know this. Now, here we are putting this Q as reversible heat source and W as reversible work source. Okay. So, this would be your du plus dq. Now, what we assume that the work is being done by the system, and hence this is going to be negative. So, you bring it here. Similarly, you are also interacting in the way that heat is being given out from the system. So, essentially this is the expression of the first law. Now, for a totally reversible process, okay, the delta S total is going to be 0. Now, if you look at delta S, what are the changes associated with this system? So, delta S total is going to be ds, that is for the system, and the heat interactions with the surrounding, which is going to be del of Qr divided by whatever the temperature of this heat source. Okay. So, that is going to be this one. So, combining the expression above, we obtain del Wrs is nothing but Trs ds minus du. So, this is something directly here. So, if you combine this expression and this expression, we are going to get this expression. Okay. Now, further we can expand this and try to come up with the integral form. So, if the reversible heat source is a thermal source, then the previous expression can be integrated. That means there is no changes in the properties of this thermal reservoir over time, okay, within the time of the interest of the process. So, that means it is so large that heat transfer can be does not alter the temperature of the thermal reservoir, and T can be considered as a constant here, TRS, TRHS. So, if you integrate this, you are going to get this is from the first equation, this is from the second equation, and this is from the third equation. Okay. So, this is from the first equation, this is second equation, this is third equation. So, that is the integral form of this. Okay. So, now let us look at some examples to make use of our understanding. Okay. So, this is the first question. This is a 1 meter cube tank that initially contains air at 1 bar and 300 Kelvin is to be evacuated by pumping out the contain. Okay, the tank contains are maintained at 300 Kelvin throughout the operation by heat transfer through the walls. So, it is maintained at 300 Kelvin. The only thing it loses out is basically the air. The compressor discharges the air at 1 bar and is operated isothermally at 300 Kelvin. So, this is 1 bar, but this is operating at 300 Kelvin. So, what is the total work done by the compressor when you take the whole amount of the gas and pumped out from the or discharge it to the air? Okay. So, what we have to do is the other thing which you have to assume is the compressor operates reversibly and air is an ideal gas. So, this is a very gross approximation, but this will ease out the problem to solve. So, we will just simply jump with the fact that this is reversible process, and essentially for this the work associated with this reversal process is nothing but the integral of VdP. So, let us consider that this is the differential work to move or pump a small amount of air delta N from the pressure tank pressure to discharge pressure, which is nothing but 1 bar, and this will be VdP. Now, this is an ideal gas. So, I can write this as RT by P okay. So, if I say this as PT and this is as PD, then this is going to be PD by PT. Okay. Now, this if you integrate, or rather if this is nothing but can be also written as the differential form. So, this is V tank divided by RT dP tank, right. Okay, so we can simplify this also by saying this as because the pressure of the tank keeps changing, right. So, the differential amount using the ideal gas equation of state is going to be this. So, we plug in back here. So, what we have is del Ws Vt by RT ln Pd by Pt, and then you can say P dt. So, the tank pressure keeps changing, is only the discharge pressure remains constant. So, this gets cancelled. Now, if you integrate this, we are going to get Vt, which is constant, Pt ln Pt by Pd minus Pt, and this Pt range from initially it was 1 to 0. Okay. So, this can be shown that this is nothing but Vt. Okay. So, this is the reversible work done by the compressor, which is nothing but 10 to the power 5 joules from the values which is here. So, let us now try to work on an example related to entropy change of an ideal gas. So, this is the question, the 10 mole of an ideal gas with heat capacity at temperature 300 Kelvin and pressure 0.3 megapascal occupy the left of an insulated vessel. The other half is evacuated. Okay, so you can consider something like this, that you have insulated vessel, okay, and this is separated by a partition, and now this contains the ideal gas, okay, with at 300 Kelvin and 0.3 megapascal. Okay. So, this is your partition. Okay. Now, at time t equal to 0, 1 kilowatt electrical heat element is turned on. So, you can consider that you have a heating element where it is turned on at t equal to 0 to, let us say, 30 seconds, which is being set here. The partition dividing the vessel ruptures at after 30 seconds and the heating element is turned off. Now, we need to find out the basically the final temperature and pressure of the gas in the vessel and so forth. So, we will assume this partition does not occupy as such volume, it is a 0 volume, and then hence when it ruptures, basically the ideal gas occupies the whole volume, right. So, now let us try to solve this problem. One of the things which we can do is we can first find out first law of thermodynamics over this system here. So, delta U is going to be Q plus W, and since there is no specific heat as such, it is basically electrical heating, and essentially this is a electrical work which is applied on the system. So, essentially we are going to put this 0 because this is corresponds to the electrical heating element, and now delta U I can write it as NCV delta T. Okay. So, what is the W here? W in this case would be your 1 kilowatt multiplied by 1 kilowatt is 1000 joules per second multiplied by 30 seconds. So, this is the work, electrical work, which is done on the system. A system is defined by this here. So, we can consider this to be system. Okay. So, what about the delta T here? Delta T is TF final minus T0, right. So, I can obtain the TF would be your T0 plus W N CV. Okay. And what about N? N is we know number of moles are 10 moles. CV we know 20.8 joules per mole, and W of course we know. T0 initially is given as 300 Kelvin. So, when we plug in these values, N is 10 moles, CV is 20.8, the value comes out to be 444 Kelvin. So that is the final temperature of the gas in the system. So now let us find out what is the pressure of the gas in the final state. So to obtain the pressure, that means what is the final pressure, okay, we can consider that since the number of since n is constant, okay, so we can use ideal gas equation and we can write it like this, since n is nothing but PV by RT. So in this case n final is equal to n final is equal to n initial, and hence we can write this as P0 V0 RT0. Okay. Now what I can do is I can get rid of this. I can write PF is equal to P0 TF by T0, and now is V0 by Vf. Okay. So let us look at again this. So essentially what I am going to consider is that initial volume which is occupied by the gas is actually half of the final volume. So essentially my system is not going to be this, but rather this okay. So what I am going to do is I am going to erase this part, okay, because essentially I am going to consider this which expands here. So actually I am looking at the volume initial, which is this half the first compartment, and then in the final one is this, the first and the second compartment. So that's a system which basically has a non-rigid boundary and it can expand, and if that is the case we can consider this to be 1 by 2, okay, and TF we know, T0 we know, P0 we know. So if you plug in these values which are available from the question, it comes out to be 2.2 megapascals. This is something which you can try to solve this problem at home. Now second part of the question is the entropy change of the gas. We can try to think that why can't we use this simply delta S del Q by T. Well, we can't, because this process we know this is not a reversible process. So how do you solve and obtain delta S? So to obtain entropy change, we will revert back to the thermodynamic equation, the fundamental equation. So that is going to be du TdS minus PdV, okay, and I can write ds as if we divide by T, I am going to get and to represent du as NCV delta T, then basically this is going to be this plus P by T dV, which I can write from the ideal gas expression, equation of state, NR by V. So I have now an expression which is NCV by T dt plus NR by V dV ds. Okay, so now I can take the n here and integrate it. So this becomes delta S by n, and this is your Cv dt by T plus R dV by V. So you have an expression of entropy for an ideal gas Cv ln Tf by T0 plus R ln Vf by V0. Okay. So in the case of this problem, we know the Tf, we know T0, we know Vf and V0, we know Cv as well. So we can find out delta S. So when we plug in this value, this comes out to be 13.9 joules per mole Kelvin. Okay. So we can multiply by the number of moles to get the total change in entropy, that is going to be 10 into 13.9 joules per Kelvin, and this is certainly greater than 0. This is also indicative of that the system or the process is irreversible. Okay. So that is the part which to solve this one of the this particular problem. Okay. Now, one can also come up with an expression of delta S in terms of PF and VF also. So, that is something you can also come up with. I can just write it down for you. So, this is going to be your delta S by N Cp ln Tf by T0 minus R ln Pf by P0. Okay. So, this is the another expression which you come if you vary T0 P0 V0 to Tf Pf V0. This is another expression you can evaluate for your delta S of ideal gas. So, in that case, if you have the pressure information, you will be using pressure information. The one which you have used is a volume information. Both would yield the same expression. Because it is a state property, and hence if the final and initial states are same for a given process, then this expression delta S, whether you use this expression, the other one, both of them should yield the same value. Okay, so now I can move to the another problem. This is a problem which is related to the forging. Consider a common problem in forging of immersing hot steel in water for hardening. Okay. Consider a process in which a 1 kg steel blade at T 800 degrees Celsius is immersed in a large vessel filled with water at 25 degrees Celsius and immediately quenched. Okay. So, you have a large vessel and a steel blade at very high temperature. Okay. So, large vessel is there maybe. Okay. So, essentially large vessel, and then this is filled with water at 25 degrees Celsius, and then you have a steel blade which could be considered like this. This is at 800 degrees Celsius, and immediately it quenched and is at T is equal to 0, you basically you put into this water and it will get quenched. So, the question is what is the change in the entropy during the process for the steel blade and the water and the universe. Consider that steel has a heat capacity of 460 joules per kg Kelvin and is independent of temperature. Okay, that is one thing which we can consider. Also assume that there is enough water in the vessel so that the water temperature does not change upon immersion. So, this remains at 25 degrees Celsius. So, how do you solve this problem? So, one of the things which we can do is we can ignore the change in volume of the steel. Okay. So, this is something which we can consider for metals for this temperature range. Okay. Let us look at the steel blade and apply this first law. So, for steel blade, so du is TdS minus PdV. So, since the volume is constant, we have nothing but this expression, and if you rewrite this, we can write in this way. Now du by definition we can write as 1 by T NCV dt. Okay. So, delta S here for the blade would be your NCV. CV is a constant, is not changing. So, essentially I can write this still as this. So, I know the N in this case is not considered to be number of moles because CV is given in terms of kgs. So, essentially if you look at this is in joules per kg. So, this is different from this which was in moles, remember that. So, the unit does make a lot of difference. So, one has to look at the units of the heat capacity in order to appropriately use this N here. So, N in this case would be in kg. So, this will be like say 1 kg, that is what the given to us, and CV is 460, and then I put this value of TF. T0 is 800 degrees Celsius for steel blade, and eventually at equilibrium this is going to be 25 degrees Celsius. Okay. So, this turns out to be minus 589 joules per Kelvin. Now, you might think about why it is negative, because again the blade is just sub part of the overall process, but even for irreversible process you can have a delta S of subsystem can be negative. So that's something which is evident from this, okay, even if it is an irreversible process. Now let us try to get more information. The second part was for the water, what is the delta S for the water. Now this is a rather tricky part. So in order to obtain this, we need to have some information for the water, but of course in the problem is nothing is given as far as the water is concerned besides only the temperature. Then we cannot use also directly simply this d delta q reversible by T. For that we need to find out this, but the process is irreversible. So what we should do, that's an important question. So how do we do that? Now one can think of because the temperature difference here for the water, so this is your water here, and so temperature difference here around this and the water is extremely large. So delta T is quite large, right? So what we can think is a kind of a thought process where basically we can devise a thought process in which the Q transfer to the water is done reversibly, okay. So eventually we know what is the amount of the heat which is transferred from the steel to water, because essentially we know the change in the delta U of the blade, and since there is no work associated with it, so essentially the delta Q is nothing but delta U. So Q is nothing but minus of delta U blade. So this we know, all right. So and then we can plug in this value to get the value of the 356 kilojoules. So this is the amount of the heat which is transferred from the blade to the water. Now this is done of course in irreversibly, but what we can do is now to calculate the entropy change of the water, we can come up with a way to find out a thought experiment where we can devise this amount is transferred in a reversible way, okay. So in that case we can write, so this is something which is a thought experiment, and in this case Q transfer to water is done in a reversible manner, okay. So with this we can find out a delta S for the water, okay. That is going to be simply the Q reversible by T, and that is what we can find it out, okay. So this is one way of doing it. This T is 273 plus 25, and then we can find out the delta S of the universe, which is delta S of blade plus delta S of water, okay. But yeah, so this is one thought experiment based delta S calculation, okay, because we are not being given any information. Otherwise if you consider there is no change in the volume, and there is no, if the other properties are not being affected, then one can also find out using the first law analysis. Also one can try to do that, but I am trying to avoid that part in this problem, but it is something you can try in different ways to solve such a problem, okay. So this is one way of approaching it, okay. So with this I think we will stop and then in the next class, which will be the last lecture of this engineering thermodynamic aspects in this particular course, I will be covering power cycles. So I will see you in the next class.